This is the math behind shell elements, and it matches ANSYS exactly. Shell elements are essential for simulating thin-walled structures like car doors or airplane skins. But there's a problem. Naive shell formulations can suffer from blocking, especially as the thickness becomes very small. Your model becomes unrealistically stiff. This happens because bending and shear aren't represented correctly. Shell must capture three behaviors: stretching in plane, bending out of plane, and transverse shear. Each comes from different physics, and if you miss any, misbehaves. Handle shear wrong and you get locking. Skip it entirely and it becomes too soft. MITC stands for Mixed Interpolation of Tensorial Components. It's a technique to fix how transverse shear strains are computed. Instead of using node values, we tie them to points along the edges. In membrane shell theory, we assume a thin shell where membrane stresses dominate and bending is negligible. The in-plane stress equilibrium is expressed in local curvilinear coordinates as partial derivatives of in-plane forces plus distributed loads. Using the Jacobian, we transform local to global derivatives. Strain components relate to displacement and curvatures of the middle surface. Finally, stress resultants follow a plane stress constitutive law with isotropic elasticity and shell thickness scaling. Let's take a closer look to classical bending theory of thin shells. In Kirchhoff law theory, the shell resists deformation through bending and twisting moments, which depend on the curvature of the mid-surface. mxx is the bending moment in the x direction. It's proportional to the curvature and x, and through Poisson ratio also influenced by the I direction. mxi is the twisting moment. It resists how the surface curves diagonally in both x and I, while d appears at this moment scale with the flexural rigidity d. It combines Young modulus, thickness, and Poisson's ratio. Since it's proportional to h cubed, even small changes in thickness drastically changes the stiffness. Introducing Mindlin-Reissner plate theory, ideal for thick shells where transverse shear can't be ignored. This theory assumes a thick geometry, independent rotations, and accounts for a shear deformation. Unlike Kirchhoff theory, the displacement field includes rotation terms, adding realism to out-of-plane behavior. Shear strains are now active. This contributes to transverse shear forces scaled by a correction factor. First, we have membrane strains, the in-plane stretching or compression of the shell. This is the most intuitive part, when the shell is pulled or compressed along its surface. In terms of matrices, we build a B matrix from in-shape function derivatives. The resulting straight displacement relation captures axial and shear deformations within the surface. Next, come bending, when the shell curves out of its original plane. This is what gives shells their elegant flexibility. We capture bending through curvature changes based on the derivatives of the shape functions representing the rotations. The B matrix here links the rotation to curvature strains. Finally, there's transverse shear, deformation caused by forces pulling layers past one another. If this isn't modeled carefully, the shell will lock, especially in thin configurations. MITC fixes this by evaluating shear not at the nodes but at special points tied to the element edges. Here's the key idea for shear. We define a covariant B matrix each tying points and map it to global coordinates using the Jacobian. Then we integrate along the edges or more accurately over areas with edge-based info. This removes locking. This is my implementation. I compute membrane, bending, and shear stiffness separately using clear mathematical blocks. Now hacks just solid FEM theory. Here is what it looks like when we run a basic simulation. This triangle bends smoothly any artificial stiffness. That's the power of MITC3. Clean theory, clean code, and no locking. Want to write your own FEM solvers or just understand how they work? If you're into FEM, SPH, CFD, remeshing, or just enjoy watching solids get squished by clever math, you're in the right place. I dive into open source solvers, GPU acceleration, and how these methods actually work under the hood. So hit subscribe, or better, hop on the mailing list at opensourcemech.com. No spam, just good stuff. And if you want to support or ask deeper questions, there's always my Patreon. Thanks for watching and happy coding!